questions before? I always take questions at the beginning for the homework assignment. Yeah.
It's 6.7 from the textbook.
Pardon me?
6.7 from the textbook.
6.7? Okay. Just tell me what it is.
It's supposed to have a field of amplitude of 5, cosine with pi.
5 cosine?
Yeah.
5 cosine. Oh, man. We'll use this one. 5 cosine what?
It's pi times 10 to the 6 times t.
10 to the 16.
Minus 3x plus 2y.
Plus 2y.
Yeah. And it's asking us to find the direction of population.
Is it in the A, Z?
Yeah.
And this is the E field?
Yeah.
Okay. I'm glad you, thank you for it. Okay, so they want the direction of propagation, they want a unit vector in the direction of propagation. What else do they want?
The magnetic field, and that's it.
Omega?
They also want the H field, and that's it.
H field?
Yeah.
Okay, so they want the H field too. All right, for this one, here's the thing. This is a little different, because you have X and Y there. You all follow me on this? So let me just tell you the way, and I don't think Dr. Wilmer's book talks about this, but he actually came up to my office and asked me about this. In general, when we have these things, usually instead of beta, there's a vector K that's actually given. K and beta are the same thing. They're really the wave number. It's how many radians per meter. But K is a vector. And K, you can use beta and put a bar over, but K has some Kx AX plus some Ky AY plus some Kz AZ. Now the units are radians per meter, as before, but what it is a vector form of beta. Think of it, the propagation or the wave number. Y'all follow me on this, class? Now, normally, when you talk about an electric field or a magnetic field propagating, this would be at the upper level courses, you would have some E naught, if it's lossless, then it would be times cosine of omega t, and then it's minus K dot vector R, where R is a positional vector. This is in the AZ direction. Here R, since we're in Cartesian coordinates, would be XAX plus YAY plus ZAZ. I'm gonna just pause for a second. R in general could be in Cartesian, it could be in cylindrical, it could be in spherical coordinates. It is just a general position vector. So this is what R is, right here. K is a vector. Y'all follow me on this, guys? Now, if you take a look at this, when you do the dot product of these things, now this is something I'm going to tell you this. This is a wave propagating in the K. Well, I'll show you how to get this. The direction of propagation, once we find the components of K, a unit vector in the direction of propagation right here is simply K vector divided by magnitude of K. Follow me? Okay, now, getting back to that, remember, this is not in the book. He kind of loosely hand waves about this. Did anybody else try this problem besides? You tried, so you understand the confusion, right? I mean, this right here causes some confusion. This should straighten it out. So if I look at this right here, I'm going to say, I want to find the direction of propagation. I showed you how to do it, but you'll notice there's a minus there. So I'm going to say minus K dot vector R are equal to minus 3x plus 2y. Everybody got me on that? I'm simply taking the last two terms there and equating them to minus K times vector R. All right, positional vector R. With me, everyone? All right, now, when I take a look at this, I have minus K, and now, if you look at this, when you take this vector dotted with this, you just get Kx times x plus ky times y plus kz times z. Y'all follow me? So here, I have minus kx times x plus ky times y plus kz times z, and that's equal to minus 3x plus 2y. Right, the first thing that's apparent when you look at this is kz has got to be 0. There is no z over here. Y'all follow me on that, class? I mean, there is no kz. Follow me? It's 0. So kz is 0. That strikes that up. Next is what? Minus kx is equal to minus 3x, or kx is equal to 3. Y'all follow me on that? And when you look, you have minus ky is equal to 2, or ky here is equal to minus 2. Go with me on this one. Y'all follow me what I'm doing here? All right, now back over here to get the unit vector in the direction of propagation. Now I go ahead and I put k up here. Well, k is vector. It's kx, and kx is 3ax minus, and then ky is minus 2ay. And now I have to divide by the magnitude. Well, the magnitude is going to be the square root of 3 squared plus 2 squared, or the square root of 13, right? That'd be 9. Well, wait a second. Did I do that right? Yeah, I think I did. 9 and 4 is 13, right? Got to take the square root to get the magnitude. All right, so let me just say this again. Here, k itself, we've discovered vector k is equal to 3ax minus 2ay. Right? And it's key that you understand that the vector direction, you'll notice how in here I have omega t minus k dot r, positional vector r. Now, if, remember, that k vector gives you the positive direction of propagation. Follow me? With me on this? What do you see from here? Well, it's actually propagating the positive ax direction, but the negative ay. You follow me? And that should make intuitive sense to you, just look at this, right? But that's how you do that problem. And that's, what else? He wants the H field, right?
Yeah.
Okay, so let's keep going on this one. Here's the E field that he's given. Now we want to get the actual phasor form of the E field. How do you get the phasor form? Well, we'll take the magnitude of 5. Everybody agree with that? That just translates perfect. We forget about the omega. With a phasor, you get rid of that. Then it's just going to be e to the minus j, and here it's going to be minus j k dot position vector r in the az direction. Now we know that that's going to be 5 times e to the minus j. Here, I'll do the dot product. I'll just take k dot r right out in front. So I have what? Minus j, and it's going to be 3x minus 2y. Do y'all follow me on that? I'm just putting k dot r up there, and it would be in the az direction. The units are volts per meter, I believe, for this one. So that would be the phasor form. Okay? Now, how do we get the H field, the phasor form of the H field, if I know the vector direction of propagation and I know the actual, does that say it's an air? What does it say if the media is?
The what?
What is it propagating through?
Oh, it doesn't say.
Yeah, it doesn't say.
Well, okay, we can determine that. Let me show you how. You see this? That's omega. Do you agree with me, everyone? All right, so if omega is equal to pi times 10 to the 6, we know that's 2 pi f as well, so we can get f, which is going to be just 10 to the 6 over 2, or 5 times 10 to the 5th. But don't worry about that. That's omega, right? Now, the actual magnitude of beta is the same thing as the magnitude of k. All right? And if you look at that, that's square root of 13, right? You agree with me? Okay. So, if we have beta and we have omega, we have the velocity, phase velocity, don't we? You agree with me, class? So what is the phase velocity going to be? Omega over over beta. Omega is pi times 10 to the 6 over beta, which is square root of 13. That phase velocity is quite a bit less than the speed of light, isn't it? Matter of fact, this is 6-7, right?
Mm-hmm.
I think Whitworth messed this problem up. All right, so we have, that is 10 to the 6, isn't it? All right, now this phase velocity is quite a bit less, and I think this is where Whitworth made a problem, because I'll tell you what we need to get is the intrinsic impedance of the media. Do y'all follow me on this, class? We have to get that. The way we're gonna get that is I'm gonna tell you, he should have put down it's non-magnetic, and I can see it's lossless, because there is no e to the minus alpha z here, so I know it's lossless. But he didn't say non-magnetic, and that causes a bit of a problem. I think he meant to. And I think also this problem's gonna have a screwy answer if you're being, if it's exact. But if you look at this right here, the phase velocity we know is really going to be equal to the speed of light divided by square root of epsilon relative if it's just a dielectric. I mean, if it is a non-magnetic conductor, I mean a non-magnetic media. Do y'all follow me? It's just going to, the thing that's going to slow it down is epsilon relative. So if you look at this, this is 3 times 10 to the 8th, right? Over square root of epsilon relative. By the way, do you all understand where I'm getting phase velocity from? All right, that's 1 over the square root of mu epsilon in general, right? If it's lossless, a lossless media. Here, I'm assuming it's non-magnetic, so that's 1 over square root of mu naught epsilon naught, which is c divided by square root of epsilon relative. That's what I'm doing right here. Follow me, everyone? Okay. Now, what does this mean epsilon relative is going to be? Take a look at this. We have the square root of epsilon relative, right? Is going to be equal to, just take a look at this. If I go ahead and I cross multiply by square root of epsilon relative, and that's going to be 3 times 10 to the 8th, right? Divided by pi times 10 to the 6th, and then it's times the square root of 13. So that's going to be 300 over pi times square root of 13. That's a big number. I don't know what that is, but it's obviously fairly significant, isn't it? Y'all with me? All right, now, how do I get, once, can Mike just give that to me? I'm curious how big that is. It's pretty big. Square root of 13, I don't know. It's 3, so it's 900 over pi. It's about 300, a little over 300. What'd you get? 300 times square root of 13 over pi. It's huge.
344.
Yeah, I think he messed this one. So 344. All right. Now that means the intrinsic impedance of the media here is going to be square root of mu over epsilon. That's really square root of mu naught over epsilon naught times square root of, really mu relative is 1, I'm assuming, over epsilon relative. And epsilon relative in this case is going to be 344. So this is going to have a very small value because this is really 120 pi, right? Divided by square root of 344, and I don't even know what that is, but that'll, whatever it is, it's going to be intrinsic impedance. What is that? 120 pi over square root of 344?
Well, 20, that's not relative, needs to be squared too, doesn't it?
Oh, yeah, you're right. So you gotta square that thing. Gosh, that's big. 344 squared, my bad, so. It would be 125 over 344, actually, right? That's just about 1, if you look. What does it come out to?
About 1.09.
Okay. 1.09 for ohms, and that means now I can get the actual value of the H field, because I have the phasor form of the E field right here. So to get the phasor form of the H field, I'll put it right under here. And then we'll get the time domain form. But I have a feeling he probably assumed the intrinsic impedance is 125. I have a feeling in the answers. Tell me if I'm right about that. So then for the H field, the way we always get it is going to be 1 over eta, right? Vector and direction of propagation crossed into the E field, right? Well, here we have 1 over eta, and eta in this case is going to be 1 about. So it's 1 over 1. Unit vector and direction propagation is that 3x minus 2ay over the square root of 13, right? And then it's crossed into the E field. There's the E field, which is 5e to the minus j 3x minus 2y a z. Y'all agree with that, everyone? Now just do the crossing on this one to get the H field. This would be the correct answer. And here, I'm gonna have, let's see if I can do this. So I'm gonna take 5 the square root of 13 out front. And then I have 3ax crossed into az. So 3ax crossed az is what? Minus ay, correct class? Ax crossed az is minus ay. So it's minus 3ay. And then ay crossed az is positive a's, right? You all agree with that? So it's going to be plus 2ax. And then you can put the e to the minus j 2x minus, or I mean 3x, pardon me, 3x minus 2y, right? And that is the H field. Now I want to tell you something about this. If you look at the H field, it has components in both x and y, not just x and not just y. Y'all follow me? Because of the crossing? This is pretty common, by the way. You're usually going to have, in general, 3 components of E and H. But here the H field has 2 components. Now, to get it back into the time domain, all right, when you do this, do it over here. I mean, what's the formal way of doing it? Remember? If I've got a phasor and I want to get into the time domain, what do I have to do?
Use a voyage.
I have to do what? I have to take the real part of e to the j omega t times the phasor form of h, right? To get h in the time domain. Y'all remember that from lectures going on? All right, so when you do this, what do you get? Well, when I go ahead and do this, I'll have the real part of e to the j omega t times h. This is the h field. I want to tell you one thing. Probably what you're going to see in Whitworth's book, if he did this right, he's going to have like minus 15 over square root of 13 here, if he got the right value for a. But he's going to have a coefficient times ay right there. Y'all follow me? It times this thing. So what it's going to come out to, I'll put it all in one time. So I'm going to have minus, I'll just do it that way. So it's going to be 5 over square root of 13, and then I have minus 3ay plus 2ax times e to the minus j, and this is going to be 3x minus 2y. Okay. Now I'll cut to the chase. You see it's e to the j omega t, we have omega, it's pi times 10 to the 6, right? Y'all, everybody follow me on this? So if I take this times this, the exponents add, don't they? Y'all agree with that? So I'm going to just put that down here so you can see it. It's the real part, and this would be E, the J, I'm gonna leave it as omega T minus 3x plus 2y here. And then I have the 5 over 13, square root of 13, and I have minus 3ay plus 2ax. And that will render me, when I take the real part of that, it's just gonna be a cosine here, so I'm gonna have 5 over the square root of 13 times minus 3ay plus 2ax here, that's the orientation, and then it's gonna be times cosine of omega t, which is really pi times 10 to the 6 t minus 3x plus 2y. And that should be the answer. Now, he may have like minus 15 over square root of 13 in there. He'll have a single coefficient and a single coefficient there. Do you have the solutions on that one?
The way he started it in the solution, he just did the curl of E is minus J into mu naught H. And took the curl of E.
You can do that. If you want to take a formal curl, you can do it, but it's easier, in my opinion, you can do that. It's much easier to just say that, if I know the vector, I've showed you how to get the vector direction of propagation. That should agree with his propagation vector. Unit vector and direction of propagation was, I erased it, but it's, what is it?
3ax minus 2ay.
Yeah, 3ax minus 2ay over square root of 13. Is that his?
I punched the numbers in the calculator and they do not match the one that he has on the back of the textbook.
This should be the unit.
That unit vector is right, the propagation is
Yeah,
right.
that part is
If the
right.
unit vector is right, here's the problem with his thing. When he did this, and he had this original formula, he had E equal to 5 times cosine of pi times 10 to the 6t minus, what was it, minus 2x, or plus, it would be plus 2y minus 3x. I think that's the form he had. But here's the problem. This omega and this magnitude of beta don't give you a velocity, a phase velocity that's equal to the speed of light in a vacuum, because he's assuming eta is 120 pi. So when I go ahead and I take the curl of h, or he took the curl of e bar, when you take curl of e here, you assume that's equal to minus j omega mu h. Well, the mu here is going to be assumed to be mu naught, right? But that won't, if you just assume mu naught, then this will not agree with this thing right here. What he has is an inconsistency. The omega over beta here should be the speed of light in a vacuum, but it's not, so he made a mistake there. Right? But doing the curl will get you it if you know what mu is. He doesn't give us mu. Do y'all follow me on this? Curl E takes plenty of time. The way I showed you to do it, if that problem was consistent, it's easier to get the unit vector doing it this way, the k vector, like this, and I don't even know how we got the unit vector in the direction of propagation. And then, once you get that, just to get the actual H field, just use this trick. Right? It's quicker than curl, in my opinion. All right, if you want to do curl, go ahead, but sometimes the curl can get a little tedious if you're in Cartesian, or if you're in non-Cartesian systems like spherical or cylindrical systems, okay?
Just to make sure I'm understanding your symbols right, that is not the actual H field, right?
Where?
This, where you have the, 5 over 30 square.
Yeah, that would be
Is
the
that-
H field, that would be the H field based on his values of beta and his values of omega. That would be the correct H field.
Okay, so then what's the difference between that?
That's
and
time domain, right?
that- Oh, my
See,
bad.
we're going to, phase domain is right here, this is time, that's the
Yeah,
observable
okay.
domain.
Yeah.
Stay up with this too, you gotta
Yeah.
keep up with this, because this stuff, if you get behind it, really gets horrifically bad. But are you with me on this one? So there's an inconsistency with the mega and beta for that one, and that's on him. But still, it's a good problem, because it shows you how to get a unit vector and direction of propagation for something that is just not a single beta and a single spatial variable. By the way, did he show you how to get the unit vector and solutions?
He did E cross H over the back.
You can do that, yeah, I don't usually recommend that, but what he's gonna say is, see, to do that, you have to know the H field, right? So you have to do the curl of E to get that. But what he's saying is, I know that power in general is equal to E cross H. I know that. So and power flows in the direction of propagation. So if I take P over P magnitude, now I have a unit vector in the direction of propagation, and that's E cross H over the magnitude of E cross H. That's a longer road if you're gonna do a curl. And so the way I showed you there with that KX business, KY and KC is the easier way, in my opinion. It's the way we do it in higher level courses too. All right. Other questions? We have a question, buddy. Yeah.
So wondering back, question number 6.46 is the last one on the previous homework.
Okay.
Says, whenever you're ready.
I'm about ready to go run up and get some more markers, but, because I really like the darker colored markers. My problem is that, in the past, the markers that they have up there are dried out. Even though they're fresh out of the box, that box has been there probably for years, since COVID started. Bear with me one second. I'm gonna see if I can just grab a box. Yeah, you're right.
That's all electrical engineering is, man.
You meant to have a quiz question.
Forget it.
Right over my hand.
Just go right. Magnetic media, question mark.
Right, the theoretical.
You just ride.
Well,
Epsilon relative
if
vertically.
you have a row, then let's say until dot dot.
Go ahead, sorry. This
This
is
is-
an epidemic right now. Everything that's been sitting around for a couple of years, it dries out, is drying out. Or,
It says a wave specified by the E field in the incident direction is,
E field,
yeah, E incident is 100 cosine times pi times 10 to the 7 t minus beta 1z,
minus what?
beta 1z.
Beta.
Beta 1z.
Oh, okay. Beta, okay.
In the,
Go ahead.
in the AX direction.
Uh-huh.
And then it says, its incident from air at Z is less than 0
Right.
to a non-magnetic media where Z is greater than 0 with sigma equals 0.05
Oh, yeah. Go
and
ahead.
epsilon relative is 9. And then it wants you to find the E field in the reflection, E field for the transmitted, and standing wave ratio.
All right. Okay, standing wave ratio is something. E reflected, what else?
E transmitted, standing wave ratio,
SWR.
and it also wants you to find the average power densities for the incident, reflected, and transmitting
Alright,
wave.
so we need P. This is a good problem, because it's gonna allow us to introduce a few things. So first of all, I'm gonna say this. Do you remember what the standing wave ratio was back in the day when you had transmission line here? SWR was what? It was usually VSWR, right? Voltage standing wave ratio. What they did is they say, if you have a transmission line, this is say Z equals 0, and you looked at the magnitude of the phasor voltage, which is the sum of the reflected and the incident voltages, you would get something like this. Y'all remember that? Everybody? This is the peak value, V max, and this was V min, right? Right. And the standing wave ratio was actually V max, phasor V max magnitude over magnitude of V min, right? Y'all remember that? Well, when we talk about electromagnetic propagation, we've got two media, and we want the standing wave ratio. Think of it this way. You've got like a voltage coming incident. Remember back here, what is this actually going to be right here? This V in general, V phasor was from V0 plus, right here. And it's going to be times e to the minus j beta times V plus V0 minus e to the plus j beta z. You all remember doing this kind of stuff? Then what they usually did is break out V0 plus, and they had this is e to the minus j beta z plus, and then the reflection coefficient at the load times e to the plus j beta z. And that was the voltage anywhere. And the standing wave ratio, when I take a look at this, you remember how to get the maximum of this? What is Vmax? Maximum possible magnitude. That's simply going to be what? V0 plus times 1 plus the magnitude gamma, right? And V min, right here, is actually equal to V0 plus times 1 minus the magnitude gamma, because gamma could be complex, right? Y'all remember this kind of stuff? And then that meant the standing wave ratio back in the day when we had this was equal to 1 plus the magnitude of gamma L over 1 minus the magnitude of gamma L. Try to refresh your memory on that stuff. How many remember that? All right. All right. Now that's, I mean, it's essential that you have some recall about stuff that you had in EMAG 1, because EMAG 2 is based largely on some of the things you've learned in EMAG 1. All right. Now, I come over here and I look at this, just think about it. If I want the standing wave ratio over here, it's really the magnitude of E maximum possible value over the magnitude of E minimum. Well, both of those two things are phasors, right? We'll talk about this in a second. So here's what I'm going to do. I'll tell you what the answer to this is. The standing wave ratio here will be the same as over there. It's simply going to be 1 plus the magnitude of the reflection coefficient at the interface over 1 minus the magnitude of the reflection coefficient. It's going to be identical as before. But what? The reflection coefficient now changes a bit. Now the reflection coefficient is equal to, it's the impedance I'm going into, or eta 2, minus the impedance I came from, eta 1, over eta 2 plus eta 1. Don't remember doing that? When we had reflection, you always go the impedance you're going into, minus the impedance you came from, over the sum of the two, right? That's the intrinsic impedance of the meteor. So we're going to do it for this one. This is a good problem. All right. So let's first, from this, let's go ahead and identify some things. By looking at this waveform, right? This is an air, right? Correct, class? If it's an air, we're gonna get a whole bunch of stuff. First off, what is F gonna be? F would, or maybe omega here is equal to what? Pi times 10 to the 7th, right? It's an air, therefore, I mean, if F here is gonna be this divided by 2 pi, correct? Or this is gonna be 5 times 10 to the 6th hertz. Do y'all agree with that? Just take that and divide it by 2 pi. Y'all agree? All right. Now after that, since it's an air, we know the velocity is gonna be c, that's an air. So we can get the actual value of beta, because since you're an air, we know that omega over beta is equal to the speed of light, if you're an air, correct, class? So I can get beta is equal to, just take a look at this, the omega, right, divided by c, correct, class? All right, what is that gonna be? So that's pi times 10 to the 7th over 3 times 10 to the 8th, right? So it's pi over 30, is that right? Class? Follow me? You got pi times 10 to the 7th over 3 times 10 to the 8th is pi over 30, correct? So that's beta. We have beta in region 1, correct, class? And so we can put that in there for beta in region 1. Now, I'm going to start here. I'm going to put E incident in the phasor domain. So E incident in the phasor domain is going to be equal to 100, right, times e to the minus j. I'm just going to leave it as beta 1 z, and it's in the ax direction. Next, I'm going to go ahead and get the intrinsic impedance. I know in region 1 it's just eta naught, or 125, because it's air ohms. And in eta 2, what would the intrinsic impedance be in this region here? The second region? This is region 1, air. This is region 2, air. What's it going to be?
JW.
Yeah, do the full one. It's square root of j omega mu over sigma plus j omega epsilon, right? When you're uncertain, just write the whole thing down. You don't know if it's a good conductor or a lossy dielectric or what. Yep.
Can you describe the relationship between eta naught and eta 1?
Well, eta 1 I got from air, right? So the square root is j omega mu, but since sigma is 0 for air, it's over j omega epsilon, right? The j omegas cancel, you get square root of mu over epsilon, that's 120 pi.
So what is eta naught though? Like
Eta naught is considered 120 pi, it's in air. It's the intrinsic impedance of free space. That's the weird reason that the naught meant nothing.
Well, I guess maybe like on the diagram on the left, like what, so is eta 1 and eta naught always gonna be the same thing when they're coming through, like?
If it's air, eta in here is always gonna be eta naught or 120 pi ohms, 377.
Oh, okay, I'm sorry, I get you.
That's all it is. And I mean, when they talk about free space, they're talking about a vacuum theoretically, but air is a close approximation to a vacuum for propagation stuff. Okay, so I come down here, and I have eta 2. Now we gotta get eta 2. So I'm gonna go ahead and put in the math. Square root of j, omega is pi times 10 to the 7th, right? And mu is just mu naught. So it's times 4 pi times 10 to the minus 7. Then it's over sigma, which is .05, is that right? 0.05 plus J omega, which is pi times 10 to the 7th, times epsilon relative, and that's 9, times epsilon naught, and you can put, I think, 8.854 times 10 to the minus 12 is probably good. It's as good as it's supposed to be. So what is this gonna be?
28.08 with an angle of 43.56.
Is that right? It's a pretty good conductor then. Say it again, 28.1?
Pretty much 28 with an angle of 43.56. 43.5.
560 degrees. Okay, now, here's something I just want to point out. It's just about a very big conductor. If I take this number right here, and I look at the value, I've got 10 to the 7th times 10 to the minus 12. Actually, I could do 1 over 36 pi times 10 to the minus 9. But I can see this, what is that going to be? That's minus 5, minus 4. It's about of the order of 10 to the minus 3, isn't it, for this one? Go ahead and do it. but-
2.5 times 10 to the minus 3.
Times 10 to what?
Minus 3.
All right, this is 1050 times 10 to the minus 3, right? Right here. This is a lot larger than that, so it's a pretty good conductor, because this is sigma. All right, you could probably just get away with saying it's 28 and angle 45 degrees, close to it. That's what it would be. It's a very good conductor. Now after that, the next thing I need is going to be the reflection coefficient. So the reflection coefficient, right, is going to be equal to eta 2 minus eta 1 over eta 2 plus eta 1. You can give me that if you don't mind. And then, while I'm at it, get the transmission coefficient, which is 2 times eta 2 over eta 2 plus eta 1. And go ahead, run the numbers on those. You got to, I encourage you to bring your calculators, because there's a lot of stupid mistakes made with calculators. I found this out.
Do we need to include the imaginary, the angle?
Has to be complex, absolutely. If you don't do it with complex numbers, you're gonna get wrong answers, big time wrong answers, because that's at an angle of 45 degrees. It's not even close to being strict real. Remember, this is eta 2, and eta 1 is just 125 to 377.
Reflection coefficient is going to be 0.9 at an angle of 174.
0.9 at an angle of 174 degrees?
Yes, sir.
And what about the transmission? It's going to be small, about 0.1. Or so.
0.1 plus 9.22 to the minus 2. Oh wait, sorry.
Put it in
Wrong
magnitude
coordinate.
next.
0.14 at an angle of 40.7 degrees, or 40.8 degrees.
1.14 at what?
Angle of 40.77 degrees, so 40.8.
Okay. We've got that. Now, we can come over here. And I can say, if that's the incident, actually I can do it right here. If that's the incident field, I know that the reflected field is just going to be incident field times the reflection coefficient, right? But it's a reflection coefficient times the magnitude E naught plus, right? And then it's going to be E to the plus J beta 1 Z AX. Y'all follow me how that coefficient up there has to be positive, because now it's reflection, it's going the other direction. Follow me, class, on this? Okay. And when you do this, give me a magnitude and angle. Take the reflection coefficient, which is 0.9, 174 times 100. Hold it, I think we can do this. That's 90. So I'm going to have 90, and it's going to be E to the J beta one, we've got beta one there, beta one Z, and it would be plus, and I wanna just mention this too. You see how I have, the reflection coefficient is in degrees, right? Can you all see that? When I multiply the reflection coefficient times E, now you get a magnitude and an angle in degrees, but you see beta and Z here are in radians. Do y'all follow me? All right, beta is in radians per meter, Z is meters, so you get radians. So you should take the 174 degrees and put it in terms of radians when you put it in this argument. Do y'all follow me? All right, because it has to be radians plus radians, or you can't, the unit mismatch, it has to be that way. So this should be in radians, so you can do what? 174, right? And then it's divided by 180 times pi, and that would be in radians. Agree? It's almost pi radians, almost, close. Follow me on this, class?
How exactly did you get 90?
Huh?
How exactly did you get 90?
Well, 0.9 times 100 is 90.
Oh, okay.
That's the only thing I'm doing, taking the reflection coefficient right here, right, times E naught. E naught is
Oh,
100.
that's 0.9. I thought you were at 6.9.
No, it's like 0. Y'all, everybody okay with that? All right. So we got that. Now we need the transmitted field. And how are you gonna get the transmitted field? Take the transmission coefficient, right? And multiply it times the incident E field's magnitude. So here, you're gonna get the transmission coefficient times the incident field's magnitude, but here it's gonna be e to the what? Minus j beta 2 ZAX. Follow me? Now you gotta get beta in region 2, correct, everybody? So how do we get beta in region 2? All right, what is, in general, how do you get beta anywhere? It's, how about we get gamma? That's alpha plus j beta, isn't it, class? So if we're in region 2, we can say 2. That's equal to the square root of what? J omega mu times sigma plus j omega epsilon, right? That's the general form. This is a pretty good conductor. You can get away with probably ignoring that omega epsilon. You're gonna get real close. But anyway, what is it gonna be? This is technically what it is, correct? Did you run the numbers on this, by the way? Did you? Or not?
I think alpha turns out to be 0 and the other one.
It ain't gonna be 0. It's gonna be the same as beta.
Maybe that's another problem.
That alpha and beta have to be about the same. It's a good conductor. You got 45 degrees there, an angle. See that for 82? That's that's a really good conductor. You're gonna see alpha and beta are about the same. When you run the numbers on this, what do you get? I pretty much can tell you, you're gonna get alpha equal to beta equal to square root of pi f mu sigma, about. Now,
They're not exactly equal to each other in the solution, but
they're gonna be
very
close.
Yeah, they're very
All right,
close.
what do you get? It's gonna be real close. What do you get for alpha?
For alpha is 0.969, for beta is
0.969, and what's beta?
1.019.
1.0,
19.
real close. All right. They're different, but very close. Y'all follow me on this? And I know that it's gonna be about that. So now, if you have that and you want the actual transmitted field right here, and I'll put the formula right here. Now I can say that E transmitted in the phasor domain. Time domain's easy to get, but once you get phasor, is gonna be transmission coefficient, which is that 0.14 times incident field, so it's 14. All right? Then you're gonna put the e to the minus alpha, which is 0.969. Z, right? Then you're gonna have that times beta, and that's 1 point, so it's e to the minus j, beta is 1.019 z, and then you've got that angle right here. But you need to put that in radians. Y'all follow me? It's gotta be in radians, and it would be added right here So it would be that, minus, so that's a positive angle, there's a minus there. Whatever that is, 40.8 divided by 180 times pi, it has to be in radians, AX, and that would be the transmitted field in the phasor domain. Does he ask for the time domain form or the phasor domain?
It doesn't specify, I think it's time to make.
All right, how do I get time domain from this, by the way? Well, what we would technically have to do, we'd have to take this times the real, times e to the j omega t and take the real part. Really, I know all I'm gonna do is break out a cosine, correct, class? When I do that in a time domain, it's gonna become simply 14, you'll still have this, e to the minus 0.969z, and then you're gonna have cosine of omega. Frequency will always be the same, it never changes. Pi times 10 to the 7th t minus, and then it's minus beta, which is 1.019 z. And then you have to go ahead and add that angle plus 40.8 pi over 180. And that would be the transmitted field. Does he give you, did he leave this in degrees in here? Because sometimes they get sloppy and just leave that in degrees.
Usually it does.
He does?
Usually, I think.
See, that's not right. You understand that? That's degrees and these are radians. You can't add degrees and radians. That should be in radians. Follow me on that, class? Just make sure you're aware of that when you're doing calculus.
Is it okay to leave it in degrees if we specify that it's degrees, like on a test or a quiz or something? Like if we just put the symbol there?
I probably will allow it, but I'm gonna level with you. Like, don't get in the habit of doing that, because if you mix these,
Yeah.
then you mix these up, then you get in real trouble with them if you're writing a program and stuff like this. Don't get used to being sloppy, believe me. That'll hurt you in the long run, big time. Okay? So that's the transmitted E field. We've got the reflected E field. Now let's go get the standing wave rate. We got the reflection coefficient over there, right? 0.9. So what's the problem? What's the standing wave ratio? It's really what? It's just like before when you had AC transmit 1 plus magnitude of the reflection coefficient over 1 minus magnitude of the reflection coefficient. Y'all follow me? Y'all remember that? So what is it gonna be? Magnitude is what? 0.9, isn't it? So that's 1.9 over 0.1, right? And that's really 19. Does he have a standing wave ratio of 19 for that one? Sure.
18.6.
19 what?
18.6, so yeah, 19.
So that isn't 0.9 exactly then. It's, see that reflection coefficient? It's probably
Yes.
0.8, so that's where the error is. But fundamentally, that's how you would get it. Just find the reflection coefficient. 1 plus the reflection coefficient or 1 minus the reflection over 1 minus the reflection coefficient is the standing wave ratio of the electromagnetic field in the air. All right. We need power in this too? Okay, so power is, I'm gonna have to erase some of this. Power is pretty straightforward in air, right? Because it's lossless. So when we talk about power in general for any wave, average power, of course, it's equal to 1/2 times magnitude of the E field, this is a propagating wave, over magnitude of beta, right? Times e to the minus 2 alpha z, then times the cosine of the angle associated with eta in that media in the AZ direction, if it's propagating in the AZ direction. Y'all remember that? If we're in air, right, air has sigma equals 0, and has eta equal 120 pi. So if we're in air, the incident power density is simply going to be 1/2 magnitude of the E field squared over eta, or over 120 pi. AZ for the incident wave. For the reflected wave, well, the reflected wave, everything's the same except power's going the opposite direction. Instead of the incident E field value here, E naught incident, now we're gonna have E naught incident times the reflection coefficient. But what this really will be is the reflection coefficient squared times the incident power density. It would be in the minus AZ direction. I'm simplifying the math. I could go ahead and put down, it's actually 1/2 E naught reflected squared over 120 pi in the minus AZ direction, but because really the only difference between this and what would be written here is the gamma squared term. Y'all follow me, class? So for this one, we'll get it in a second. And finally, the P transmitted. Now I'll tell you this much, when you have normal incidents like we do, transmitted power has to be the sum of the incident power minus the reflected power. You can get it from the two above. You can say it's just P incident minus P reflected. Or you can say it's simply the transmission coefficient times E naught incident, right here. It's gonna be that squared over the magnitude of A to 2, right there. And then it's gonna be times the cosine of A to 2. And then it will be E to the minus 2 alpha Z, this will be alpha 2, in the AZ direction. Now the reason I put all this stuff in there, this is the cosine of the angle of alpha 2, not alpha 2. I mean of A to 2, pardon me. You all with me on this? If you look at this, this is easier to do than that. If you got incident power minus reflected power, that's transmitted power, if you're just looking for a magnitude. This is the general form for any depth into that region, because it's got Z in there. So if you look at this, you'd say P transmitted, right here would be equal to, and this has actually got 1/2, right here, it should have 1/2, right there. It's gonna be 1/2 times magnitude transmission coefficient times E naught incident squared over magnitude of A to 2 times cosine of angle A to 2 times E to the minus 2 alpha Z, AZ. So if somebody can help me with this, E naught incident was 100, right? So it'd be 100 times, that was, I think, 0.1 about, roughly, right? Gamma, I mean, the transmission coefficient was about 0.1, correct?
0.14, yeah.
0.14? Right, if you take 0.14 and square it, I mean, take 0.14 times 100 is gonna be 14. Take 14 and square it for this one. And divide by 2, and divide by magnitude A2, and I forgot what it says, 28 or something like that. I don't remember exactly.
28.5, yeah.
And then that angle is about 45 degrees, so cosine of 43 degrees is about 1 over square root of 2. When you do that, give me the coefficient there.
2.55.
2.55 times 10 to the, is it just 2.55?
Yeah.
All right. And then it would be times E to the minus 2 alpha, and alpha is about 1, right? 0.96 in this one?
Yeah, 0.96.
All right, what do you get 2 times that is what?
2 times.
0.92, that's,
18.
so it's 100, what? 1.8 something, right?
1.9.
No, 2 times 0.92 is gonna be
1.84.
1.8, huh?
1.84.
Z, and this would be in the Z direction, and that would be watts per meter squared. And for this one, remember E naught incident is 100, so can you give me the incident power density? You're gonna see that's gonna be real close to this minus this. So what do you get for this one right here? Just 1/2 times 100 squared, that's 10,000, so 10,000 over 2 divided by 125. Okay. 13.26 watts per meter squared. All right, in the AZ direction. What does this come out? Just take gamma and square it, multiply it by that. Gamma is 0.89, is that reflection coefficient?
10.74.
This is 10.74.
That's what I'm getting.
So, and it's got a minus AZ, it's propagating the other direction. If you take 13.26 minus 10.74, what do you get?
2.56.
About that. So that's, I know there's probably some, round off errors, but that's how you get it. I think that's it. Is that everything that they asked for?
That's everything.
I got one more question for you. This is the kind of stuff I'll ask on a Friday quiz. What's the wavelength over here gonna be? What's fundamental? We can get it a lot of different ways, but what's wavelength fundamentally? 2 pi divided by beta, right? Do we have beta? Sure do. So this would be 2 pi over beta in region 2. I don't know what that is exactly, but somebody can tell me. Y'all follow me on this? All right, I've got alpha, I got beta, I got wavelength, I've got basically everything I need in this problem. I've kind of characterized everything possible: incident power, reflected power, transmitted time. I didn't get the H field, but just to be complete, if I asked you for the H field in the transmitted region, what would you do? Huh? How do you get H field? Remember, this is a plane wave propagator. What's the secret?
H equal to 1 over 8 over 1.
Right, H in general is 1 over eta, right? Unit vector direction propagation crossed into the E field. Do we have the E field in region 2? Yes, right, it's phasor form. Do we have eta in region 2? Yes, but I'm gonna tell you one thing about this. When you do eta, put a magnitude and then a phase angle. All right? Now, when you take that phase angle upstairs, it becomes negative J back. Follow me, class? All right. Y'all see this? Everybody? Okay, that's real important because that phase angle is going to come up here, it's negative. Then you have this cross this will give you the orientation of the H field. But now there's a negative phase angle, so no longer are E and H in phase. There's a phase difference when you're in a lossy medium. Maybe we should do that just to make sure you know how. So let's go over here and let's do it in the phasor domain. First, eta 2 was 1 over, I'm going to just say it was 28 about, and the angle here was e to the j, I'm going to say it's about 45 degrees. It was actually 43 something, right? We'll leave it like that. Unit vector and direction of propagation is AZ, right? Crossed into the E field. Well, the E field in region 2, I don't know where it is. Did I write that thing down? Yeah, there it is. There it is, 14, right? It's 14 times E, I'm gonna leave it as just minus alpha Z. I know it's alpha in region 2, but I'm trying to minimize the clutter. And then it's gonna be E to the minus J. I'll leave it as beta in region 2, beta 2 times Z. And it's going to be minus, and then I'm going to be sloppy. It's 40.8 degrees, but it should be in radians. 40.8 degrees. I'm going to make sure I put a degree there, right? Y'all with me on what I'm doing? Now, pay attention to what I'm about to do. I'll modify this a little, and I want to make sure everybody sees this. Take a good look at this and watch. Now, when I take this, I said it's 45 degrees. It's 43, but somewhere, I'm going to take it upstairs. What happens? Now I get, this becomes e to the what? Minus j 45 degrees. Y'all follow me? It was positive down there, but you flip the end, if you go from denominator to numerator, the angle flips, right? Now, I can add this in here, can't I? You'll see how that's minus, right? there's a minus times minus, that's plus, so I'd actually take this 45 and subtract from that, follow me? And you're gonna get a positive something, positive like about 1. Positive 5 degrees. Now, when I do this, and this is actually in the x direction, right? Now when I take a look at this, I have 14 over 28. It's the magnitude of the H field in region 2, correct, class? So I'm going to have the H field in region 2 has a magnitude of 14 over 28, or 1/2. Right? Now I have AZ crossed AX, which is AY, correct? Z cross. So this is in the AY direction. Order doesn't matter here. It's e to the minus alpha z. Alpha is about 1, right? It's 0.92 or something like that. Then I have e to the minus j beta 2. I'm just going to leave this beta 2 here. Times z plus 5 degrees. And now I want to take it into the time domain. So this is phasor. Now, what happens when I'm, do y'all agree with that, by the way, what I put up there? How do you get it into the time domain? Technically, I multiply by e to the j omega t, right? And take the real part of that, multiply. But really, what I know enough right now, I'll just take one look at this, and I know the magnitude is going to be 14 over 28, or 1/2, right? It's going to be decaying as e to the minus alpha 2z, whatever that is, And then here, now, I know it's propagating in the z direction, and this becomes what? Cosine, right, of omega t, got omega over there somewhere, minus beta z minus 5 degrees. Minus beta 2z minus 5 degrees, but it should be in radians. I'm going to put radian here. And this would be in the AY direction. And that would be the H field. It's 1/2 is the magnitude, kind of nice. Y'all agree with that?
Where did the negative go for the AY? Wasn't it to the negative AY direction?
Well, AZ cross AX is positive AY, is it? Z,
Right.
all right,
Yeah.
so not negative, it's positive. Okay? And that's about all she wrote for that problem. But I want to make sure you understand how to get all the things involved in a problem like this. This is a good problem, by the way. It's involved, got a lot going on. All right. Now today, what I was going to do is oblique incidence. That means not normal. Let me explain this. I don't think I'm going to have enough time to do justice to it. If we have a wave coming in, when I mean normally incident, it's basically striking the surface, or the vector striking the surface, or the orientation of the wave's propagation, and the surface themselves have a 90-degree angle to them. It's coming right at it like this. The wave is propagating this way, it strikes there, so it hits normal and it reflects back. That's normal incidence. Oblique incidence is when the wave, if I use the floor as an example, suppose I have an electric field this way and H field this way propagating. Now it's hitting at a non-normal incidence. Y'all follow me? When it happens to be hitting at a non-normal incidence, we talk about two types of polarization. One is perpendicular and the other is parallel polarization. Because if you think about this, now look, if I have, this is my electric field and it's propagating in this direction and hits the floor. You see how this is in the plane it's striking? It's parallel, right? Y'all follow me? Or it could be this way, as if it's coming in and hits, then there's a portion of the E field that's perpendicular and a portion of the E field that's in the plane. So I'm going to try to do justice to this by talking about the way Dr. Wentworth does. I'll be consistent with his notation. And in general, I'm going to say one other thing. A lot of times in the real world, when you're doing electromagnetic engineering, you're working with antennas, they don't use parallel and perpendicular. They use horizontal and vertical polarization, right? Because that's more common to engineering. It's very obvious what vertical is, very obvious what horizontal is. So you'll see that terminology used. I have two regions, this is region 1, this is region 2, and I'm gonna do this consistent with Dr. Moore's book. And this is gonna be the Z direction. This will be the X direction. Now, if I have an electromagnetic wave, and this is the way it's coming in, like such, and this is the angle of incidence, it's called right here. It's going to strike in this direction. But the electric field, I'm trying to do this with a color marker. So this, the electric field is actually going to be out of the board for this one. All right? Now that's the electric field right here. And then the magnetic field has to be perpendicular to this. So E's coming out, E cross H is direction of propagation. The magnetic field, and just don't make it one piece. Magnetic field is going to be perpendicular to that, so the magnetic field is in this direction. And this is the direction it's propagating. Drawing this real well, but I hope you can appreciate this. You all follow me? The E field's out of the board, the H field's in that direction. When it strikes this thing, there's a reflected wave. And the reflected wave is going to come. We're going to see the reflected wave, the angle of reflection is the angle of incidence. And it's assuming this surface is planar when it strikes. And there's also going to be, here you're going to have an electric field coming out of the board. This would be the incident field. This is the reflected field coming out of the board. And you'll have an H field too, it's coming out, so E cross H is the direction of propagation. And it's propagating that way, so H is up. Because it's propagating this way. And you're gonna have a transmitted field. Now this is in your book. And this is gonna be beta transmitted. And you're going to have an electric field. Transmitted electric field sticking out of the board. And you're going to have an H field into the board. Or in the plane of the board, I should say, not in the board. This would be the transmitted H field. So I hope you can appreciate what I've drawn there. It's in Whitmore's book. We'll tell you where. Last section of chapter 6. What I'm showing you is drawn on page 361 on the top, figure 6.21. So now, what I have to do, I'm going to run out of time. I'm going to go through this next time. All right, you can read ahead on this. But what I have to do is mathematically express the E fields and the H fields in the two media, and then show you how we get reflection and transmission coefficients. We'll be talking about something called Brewster angle. How many of you know the term Brewster angle? Or critical angle? No? From physics, didn't you guys know physics? All right, we'll be going through that, and it's going to be this upcoming lecture on Friday for the quiz. It's going to be probably the most complicated that you can encounter, because it's going to have a lot of different things going on that include a lot of cross products and for vectors that are not in one direction. But please be here on Friday. It's going to be a complicated lecture. I'll tell you that. Okay. See you Friday. Any questions? For the quiz, remember it's everything. I'm not going to give you anything on oblique incidents, but everything up to what we covered today. The homework and stuff like this, you should know how to do it. And my advice is know how to do the homework real well. Make sure you know how to do that.